I was up late last night. I think it's mostly just a scratch.
Okay. Hello everyone. Good morning. Welcome to our lecture today. Today we will introduce some concepts about congestion control. At first, can anyone discuss with me when congestion can happen in communication network?
Like too much traffic going onto the network for individual nodes to sort of deal. Same thing with like a highway where there's too many people leaving their house at the same time.
Yeah. Perfect. Any other answer? You agree with them? So, in this lecture, we will learn why congestion occurs and how it is controlled in transmission control protocol. Actually, as we know, in statistical multiplexing, in circuit switching and packet switching, that each user has a varying data rate. Sometimes you need low data rate, sometimes you need high data rate. So at some times the traffic demand might exceed the capacity of our communication network. And if the traffic demand exceeds the capacity of our communication network, this means that our packets will stay in the buffer. And if the buffer is overloaded, so the buffer will have to drop some packets that exceeds the size of buffer. And if we drop some packets, this means that these packets will not be delivered to the destination. So the destination will send retransmission request to the sender, and the sender will resend these packets again. So this is the process, what happens if congestion occur in our network. So as you can see, congestion can lead to two accidents. The first one may lead to packet loss, and for sure it will lead to delay. So the network will, if we have congestion, the network may suffer from packet loss or delay or the both of these accidents. The first congestion accident happened in communication network was in 1986 in USA. So after this accident happened, the network engineers know that we must have congestion control over our network. So that's why the communications engineers designed the transmission control protocol. So transmission control protocol is used to provide congestion control over the network. Everything is clear till now? Okay. Actually, we have different variants of TCP. We have different versions of transmission control protocol. As I told you, congestion lead to packet loss and or delay. So based on these accidents, we have packet loss based transmission control protocols, and we have delay-based transmission control protocol. In our first version, which is called TCP Tahoe, okay, it was packet loss TCP protocol. It defined congestion as packet loss. So if packet loss occur, we have congestion. This was our first version of the transmission control protocol. In TCP Primo, we made further improvement in this protocol, but it is still packet loss based transmission control protocol. After that, further improvement, we have TCP Vegas. So in TCP Vegas, the congestion is defined in terms of delay. So we start to have delay-based transmission control protocol. And the reason for this, in the past, the using of buffers to store the packets that exceeds the network capacity was not used in market as in 1995. So in 1995, the technology of buffering and the technology of storing packets and retransmitted was advanced. So in the past, if your packets exceeds the network capacity, drop your packet. Okay. With further improvement in the technology, we have some buffering technologies. So we were able to, we can store the packets that exceeds the network capacity in a buffer. And once the channel become idle, I can transmit the packets in the buffer. Okay, so this is the reason in TCP Tahoe and TCP Reno that they define the packet, the congestion as packet loss, and starting from TCP Vegas, we start to introduce the delay as one of the definition of the congestion. Okay, with further improvement, we reach to cubic TCP, which define the congestion as a function of loss and delay at the same time. Okay, so at the end, we can define the congestion as function of packet loss and delay at the same time. To understand the congestion control and its operation, let's define some concepts or some ingredients, some definitions. Okay, when a user, we have a sender, and for sure we will have a receiver. The sender will send packet to the receiver. Okay, the receiver, once the receiver receives the packet in a correct way, it must send acknowledgement message to the sender. Hi sender, okay, I just received your packet in a correct way. Okay, the time between the sender transmits its packet and the receiver reply with acknowledgement is called round trip time. Okay, so this is the first concept, end-to-end control via feedback. So acknowledgement packets sent from destination to source, and the time between the packet one to be transmitted to the receiver and sender receive acknowledgement from the receiver is called round trip time. Okay, this is our first definition. Okay, but let's have a discussion. Do you think this is a good way to transmit one packet? And you reply to me, okay, I received it. After that, I will transmit my second packet, and you will reply to me, okay, I received it, and go on. This is a good way of communication.
Yeah. But can you send more than one packet at once?
I can send what?
More than one packet at one time.
Okay.
So you send like,
Okay.
and then you can order, receive the acknowledgements, like one that. You send them all at once, but then you receive the acknowledgements.
Okay. This is one solution. Any other solution? Okay.
Is that an acknowledgement packet for every single packet you send?
Every single bucket must have its own acknowledgement.
Double it. Or double it how much is being sent.
Hmm? Okay, so what is your solution? I don't have.
Just send one acknowledgement after you receive all the packets.
Okay, but what if we have a problem in bucket 2, for example? We send bucket 1, 2, 3, and you are the destination. You send me back acknowledgement for which means that the 3 buckets are received in a correct way. Okay. What if we have a problem in bucket 2? And remember, you will send only one acknowledgement for the 3 buckets.
It sends a packet for every time you lose or a drop packet or get an error with the packet on the receiver. You could send a, hey, you messed up.
So you will reply to me and send that the acknowledgement will include that we missed bucket 2. Indicate, okay. But what if you don't mention in your acknowledgements that we missed bucket 2? Yeah, so if we have a problem in bucket 2, and if you have a problem, you will not send acknowledgement. So I will have to resend the 3 buckets again. Okay, okay, let's discuss. So one of the solutions is by using sliding window based control. We can call it congestion window. Okay, in congestion window, each sender determines how many packets the sender is allowed to send before waiting to receiving an acknowledgement. So, for example, we have a sender here, and we have a destination. This is the sender, and this is the destination. And for example, the congestion window of the sender is 3 packets. So you are allowed to transmit 3 packets, okay, before receiving the first acknowledgement from the receiver. So you send acknowledgement. So here, bucket 1, 2, 3, and you will receive acknowledgement 1. While you are sending acknowledgement bucket 4, you will receive acknowledgement of 2. While you are sending bucket 5, you will receive acknowledgement of 6, and so on. Okay, this is your congestion window. You are not waiting for receiving the acknowledgements of the receiver, but you must wait. If you transmit 3 buckets without receiving any acknowledgement, this means that there is a problem in the network. Okay, so after sending 3 buckets, you expect to receive the acknowledgement of the first bucket. Okay, after while you are sending bucket 4, you are expecting to receive the acknowledgement of bucket 2. Okay.
It doesn't matter, it was the same problem we had before. So like once you get past the first 3, you're just sending.
Yeah, but this is the way that we can confirm that our packets are transmitted in a correct order or in a correct way. Okay, so how can I know that what I send is received by the destination in the correct way. This is the only way. Okay, as you know, as we discussed before, asynchronous services allow delay but don't accept errors. For example, if you are making web browsing on Facebook, for example, you can one day, can you imagine that when you go to your profile and you posted an image or picture yesterday, can you go and in another day and you don't find this image? No. If you deleted it or if Facebook removed it, okay, but in normal days, no. Can you go to Facebook and you don't you find that you have Twitter, for example? No. So error is not permitted in synchronous service, in web browsing, in sending emails. So one way to make sure that we don't have errors is by receiving acknowledgement from the destination. What we do now is to organize how we can communicate, how we can receiving this acknowledgement. At first, you have to send one packet and receive one acknowledgement. Send one packet, receive acknowledgement. Now, through using sliding window-based control, okay, you don't have to wait to receive the acknowledgement of the packet that I sent to the receiver to send the second packet. No, you have congestion window. This congestion window determines how many packets you can transmit to the receiver before waiting for an acknowledgement. For example, we here have our sliding window is 3 packets, so I can transmit 1, 2, 3.
I have a question.
Okay.
Does order matter? Because like, what if you send packet 1 and you don't receive an acknowledgement, but you've already sent packet 2? So then you have packet 2, but you don't have packet 1. But what if you needed packet 1 first?
Okay. And for the sender, I will for sure I will send by order. Okay, as I have data and I divided this data into buckets, and so I will transmit my first bucket, second bucket, third bucket. Okay, this is the logic. Okay, but as a destination, as we know from routing, okay, buckets take different ways to reach the destination. So may bucket 2 reach to the destination before bucket 1 arrive. Okay, so as a destination, okay, the destination will make bucket reordering using the sequence number in the transport layer, and once it receives certain bucket, it will send acknowledgement for bucket 2. It will send acknowledgement for bucket 1. And actually, what happened in real life, we for each bucket, we set round trip time, expected round trip time. For example, I send 1 bucket to you, and I expect that you will reply with acknowledgement for this bucket within 5 seconds. Okay, so I am waiting for 5 seconds to receive acknowledgement from you. Okay, so if these seconds or the round trip time is bad and you didn't receive acknowledgement from the receiver, this means that there is a problem in the network. Okay, so as a sender, it's logic to send in order, as you don't have to send the bucket 2 before bucket 1. Why? But as a receiver, because of routing, this may happen that receiver receives bucket 3 before receiving bucket 1. Okay, so the receiver will make reordering using the sequence. Okay, so returning back to the sliding window based control. So here we determine how many packets that we can transmit before waiting for the receiving the acknowledgement of the first packet. Okay, okay. What happens if I send 3 packets And after that, I received 3 acknowledgements for these 3 buckets. This means that the network is in either case. What I send is what the receiver receives. Okay, so let's try to increase our congestion window. So instead of sending 3 buckets and wait for the first acknowledgement, can we send 4 buckets and before waiting the first acknowledgement? Okay, and go on. So we will send 4 buckets, and if we receive 4 acknowledgement, this means that the network is idle. So let's try to increase our congestion window to be 5. Send 5 packets before receiving the first acknowledgement. What if we have packet loss? Stop. We must readjust our congestion window. So if no congestion, the sender increases the window size by a constant. By 1, by 2, by 3, by a constant. If we have congestion, the sender will divide the window size by a constant. So instead, if we have congestion window is 4, and we have congestion in our network, we can reduce the size divided by 2, for example. So we can reduce the size to 2. Okay, and so on. Everything till now is clear. Okay, perfect. So as I told you, we can define congestion by packet loss or by delay. Okay, we have packet loss based congestion protocols and we have delay based congestion protocols. In packet loss congestion protocols, if I send packet 1, 2, 3, 4, 5, 6, 7, 8, and what I receive is acknowledgement for 1, 2, 3, 4, 5, 6, 8. I didn't receive acknowledgement for packet 7. Okay, and its round trip time is over. What does this mean? Yes. So if you send packet 1, 2, 3, 4, 5, 6, 7, 8, you are expected to receive 8 acknowledgements for each packet. Okay, so if you receive acknowledgement for 1, 2, 3, 5, 6, 7, 8, and you didn't receive acknowledgement for packet 4, and its round trip time is over, so we lost. There is packet loss in this case. In this case, the sender will determine that there is a problem in packet 4 and I have to retransmit it again. Okay, this is what happened in packet loss based congestion. In simple idea of packet loss based congestion. In delay based congestion, the sender timestamps packets. For example, the sender will measure the round trip time during the idle channel, during no congestion happen in the channel. And this round trip time will hold round trip time minimum, which is the minimum round trip time. We don't have congestion, so the time between sending the first packet and receiving its acknowledgement is very small. Okay, and we'll measure after that if we have congestion. Okay, we'll measure the round trip time, the time before sending the packet and receiving its acknowledgement. For sure, the difference between the round trip time in the current case or now and the round trip time minimum is an indication for the delay. For example, if in either cases I receive acknowledgement within 1 second, but in my current case now I receive acknowledgement after 3 seconds. Can anyone measure the delay? 2 seconds. Okay, So this is how we can measure the delay. We can determine the round trip time, the minimum round trip time in the cases, in ideal cases, in the cases with no congestion, and compare it with our current round trip time. Okay, if our round trip time minimum is 1 second and my current round trip time is 1 second, this means that no delay. The channel is idle. If the round trip time becomes 4 seconds, this means that we have 3 seconds delay, and so on. Okay, so delay can be determined by comparing our current round trip time with the minimum round trip time. Okay, one way. Let's now talk about the packet loss based transmission control protocol. One way to that the receiver can tell the sender that we have packet loss or we have a problem in certain packet is by using duplicate acknowledgements. For example, I transmit packet 1, 2, 3, 4, 5, 6, 7, 8. And there is a problem in packet 4 as in this example. Okay, so the receiver will reply with acknowledge 1, acknowledge 2, acknowledge 3. In this example, sorry, there is a problem in packet 5. Okay, so the sender will reply with acknowledge 1, acknowledge 2, acknowledge 3, acknowledge 4. Okay, and we have a problem in packet 5. So we will duplicate the acknowledgement, acknowledge 4, acknowledge 4, acknowledge 4, until the sender will see that, oh, I received duplicate acknowledgement of packet 4. So which means that there is a problem in packet 5. But in this case, the receiver has to send packet 5 again, by packet 6, packet 7, packet 8. You understand this idea? So here the sender send packet 1, 2, 3, 4, 5, 6, okay, and they will send 7 and 7, 8. Okay, so the receiver will reply with acknowledgement 1, acknowledgement 2, acknowledgement 3, acknowledgement 4. We have a problem here in packet 5. So the receiver will detect that there's a problem in packet 5. So we'll reply with duplicate acknowledgement of packet 4. So the receiver will know that, okay, there's a problem in packet 4. Okay, so I will resend again packet 4, 5, 6, 7, 8. How we can overcome this problem, as I already sent packet 5, 6, 7, 8. So I don't have, and the problem was in packet 5. Okay, why I have to send packet 6, 7, 8 again? Okay, we can manage this process through using sliding congestion window. So don't transmit 8 packets. Don't make your congestion window very large. Okay, because if there is a problem happen, you will retransmit many packets. Okay.
Is there any way you could like assign an error bit to each packet? Like let's say you do 6 packets in a row without sending the receiving back, and then you have an error bit attached to each packet, and then your 7th packet will just be a sequence of error bits, and then send that back and check it, and if it's inconsistent with what the error bits they expected, we send them 6.
Okay, so you propose that, and this happened in real life. In each packet, we add additional bits, and we make some mathematical operation over these bits at the sender, and send the packets with the additional bits to the receiver. At the receiver, the receiver has the same additional bits and will do the same mathematical operation. And will compare its result with the forwarded result from the sender. If they are the same, this means that the packet is correct. If they have different results, this means that some bit errors happens during the transmission in the channel. Okay, this happened, but I want to inform the sender that there is a problem in packet 6. And this is what happened now. I sent 1, 2, 3, 4, 5, for example. Okay, and the receiver replied to me, acknowledgement 1, 2, 3, 4. Okay, and there is a problem in packet 5. Okay, so the receiver will reply to me, acknowledgement 4, acknowledgement 4, acknowledgement 4. It will duplicate it for 4 times in bracket. Okay, so I will understand yet there is a problem in packet 5. Packet 5, so I have to retransmit again. Another option that the sender can determine that we have a problem in packet 5 is measuring the round trip time. We called it time to live. After this time, you are considered as dead, packet dead. Okay, so for example, if you have a child and this child was playing outside and and he didn't return back after 3 hours, 4 hours, you will call the police. Oh, help me! Where is my child? Okay, this is what will happen for the sender. The packet is our child, and it must reach to the destination within 5 seconds, for example. If it is now our 7th second and we didn't receive acknowledgement, this means that we have a problem. Okay, so we transmit. Okay.
So what if with this, like, what if there's only supposed to be 4 packets sent? So then the receiver's like waiting for the 5th packet, but there was never 5 packets that were meant to be sent. They're just going to keep sending that acknowledgement 4 out.
Okay, so here your question is, we have only 4 packets.
Yeah, like if there's only 4.
Okay, so there is no error in the channel here. Okay, so the receiver will not wait for packet 5. As I told you before we start the transmission, we make something called flow control. We agree about how many bits that I will transmit to you per second. Okay, so the receiver know how many packets it should receive from the sender before the start of the transmission. Okay, any other questions? Okay, so one way, as you can see, is to duplicate acknowledgement to inform the receiver that we have a problem in packet 5. We will duplicate acknowledgements for packet 4. This what happened here in TCP Reno. If you remember, TCP Reno is packet loss transmission control protocol. What will happen, as I told you, we have congestion window. For example, we have 5 the size of the congestion window. We can transmit 5 packets before receiving the first acknowledgement. Okay, what happens if we send 5 packets and we receive 5 acknowledgements, send 5 packets, receive acknowledgement in a correct way? The sender will try to increase the congestion window by 1. So it will be 6. So we will send 6 packets and receive 6 acknowledgements. If we receive 6 acknowledgements, we will increment our congestion window by 1. So it will be 7. We will send 7 packets and waiting for receiving 7 packets, 7 acknowledgements. If this happens in the correct way, we will increment our congestion window. We send 8 packets, but we have loss. Wait, there is a problem in a network. So we will reduce our congestion window to the half, divided by 2. So it will be 4. Reduce the size of congestion window. Okay, and repeat the process. So if the network is in either case, no congestion, we will increase the congestion window. Okay, if we have congestion, if we have problem in the network, we decrease the congestion window. Okay, this what happened in the TCP Reno. We have TCP Vegas. TCP Vegas is another type of transmission control protocol. It is delay-based congestion. We measure round trip time. The round trip time includes the propagation delay between the sender and the receiver. And if we have here, we have middle mode here, and we have buffering or queuing. So it is measured in the round trip time. So the round trip time equal to propagation delay plus queuing delay. In the TCP Vegas, as I told you, it will measure the difference between the data rate. How we can measure the data rate? By multiplying our congestion window by the difference between the round trip time in the minimum in the idle case by the round trip time at our current moment. Okay, if our data rate difference is small, this means that our round trip time in our current case now is very close to the round trip time in the idle case. So, which means that no delay. Okay, but if the data rate difference is large, this means that we have large delay, which means that our round trip time is more than the minimum round trip time. Okay, so based on this equation, based on comparing our current round trip time and the round trip time minimum in the idle case, we can determine if we have a delay or we don't have a delay. Okay, so TCP Vegas tries to maintain instantaneous data rate, make our data rate close as possible to the maximum rate, as the maximum rate will be the congestion window size divided by the minimum round trip time. So this is our maximum rate. So in TCP Vegas, we try to maintain our rate close to the maximum data rate. How can we control this? By defining threshold values for the data rate difference. We define alpha and beta. So and these thresholds are given in the design of the network. Okay, so we have if alpha less than gamma less than or equal beta, this means that our network settings is an idle case, no change. Okay, if gamma, which is the data rate difference, is greater than beta, which is given in the design of the network, we will decrease our congestion window size by 1. If gamma is less than alpha, we will increase the congestion control by 1. So as you can see here, in order to maintain our data rate close to certain data rate, we can adjust the congestion window size based on the given parameters in the network design. So TCP Vegas try to make the network have less fluctuations in data rate. Okay, so again, as a summary for transmission control protocol, the use of transmission control protocol is to try to overcome the problems that can happen from the congestion. We have two problems, packet loss and delay. For packet loss, in this case, we want to retransmit the packets again. How can we know that we have packet loss? Through using packet loss based transmission control protocol, such as TCP Reno. If we have packet loss So using duplicate acknowledgements, we will know that we have a problem in this acknowledgement in this packet. So we will retransmit this packet again. In congestion delay, how can we overcome the delay? By adjusting the congestion window size to try to make our data rate, achievable data rate, close to the maximum data rate. Okay, everything is clear to you till now? You understand the main concept of the congestion control. In our next lecture, we will understand how we can use congestion control to maximize the network utility. We have what is the network utility? Maybe increasing the throughput, increasing the data rate, minimizing the delay. This will be the topic of our next lecture. We still have 10 minutes before we finish. I want to ask you, did anyone do the digestra exercise? You didn't do it? Okay, so let's do it together, and this will be the last thing in our lecture today. So it was this one. Anyone has any question about the congestion control topic today?
What is like used today? Is it like standardized across all?
Yeah, in our lecture today.
Okay.
My question is about, anyone has any question about our lecture?
No, I'm saying like what protocol is used today now? Is it the cubic one that's used?
Transmission control protocol.
Yeah, like which is used.
Just because cubic was the last one that showed, so 2005 cubic said it was. Is that the most
Yeah,
relevant?
like the standard now.
Yeah, for now, cubic, yeah, for the cubic TCP. As we know, we have delay and packet loss, and delay can occur at the same network at the same time. Okay, so our packets, some packets may suffer from delay, and some packets may suffer from packet loss. So we must be able to deal with these two accidents at the same time. So the used transmission control protocol in the commercial now is the cubic transmission control protocol. Okay, so let's discuss this problem. We have here 1, 2, 3, 4. And we want 2, 4, 1, 1, 3. Okay. Let's discuss together how to solve. We want to go from 1 to 4. Okay. So 1, 2, 3, and 4. We will start with 1. Okay. So 1 can reach to itself with 0 cost and through destination 1. At first, can anyone tell me who are the neighbors of 1? 2 and 3. Okay, for 2 to reach to 1, what is the cost? 4, which is the link cost plus the cost of 1, which is 0. Okay, so 4 and the destination 1. For 3 to reach to 1, 2 plus 0. Hang on, please. Okay, 2, 1. For 4 to reach to 1. So infinity, and the destination will be -1. Okay. After that, which one we will select? 3. Why 3? With minimum cost. Perfect. So now 1 will not change. Okay. Who are the neighbors of 3? 1, 2, 3 are the neighbors, but we will not check 1 because it's already visited. We will check 2 and 4. Okay. What about 2? 1?
One plus 4.
1. We are checking the cost of 2 to reach to 3. 2 to reach to 1 through 3. Okay. So what is the cost? 3? 3. Why 3?
Cost of 3 is 2, and then it's 1 per travel.
Okay, so cost of 3 is 2, and the length is 1. So it will be 3 through. So we have the minimum between 4 and 1 and 3 and 3. Which one we will select? 3 and 3. Okay, so we will select 3 and 3. Okay, and node 3 will not change. And what about node 4? 1 plus 2, which will be 3. Through network 3. Okay. After that, we will select 2. Okay, no problem. 1, 3, 2. Okay, so who are the neighbors of 2? So the neighbors of 2, we have 1 and 3 and 4. 1 is already visited, so it will be the same. 3 is already visited, so it will be the same. We are at no now, so it will be the same. We will check 4. 4 to reach to 1 through node 2. What is the cost? It will be 3 plus the cost of 2. So 3, cost of 2 is 3. So the minimum between 3 and 3 and 6 and 2. Which one we will select?
3 and 3.
3 and 3. And for sure, if we select 4, nothing will be changed as we already visited 1, 3, and 2. So already for source 1 to reach to node 4, so node 4 will communicate with 3. Okay, with node 4, this is node 4. Will communicate with node 3, and node 3 will communicate with node 1. This will be our minimum cost best to reach from node 1 to node 4. Everything is okay with you? Okay. See you next week. Have a nice weekend.
Did you do yesterday your day off?
No. No, not that day. Yesterday.
How come?
I came to university. I have some experiments to do, so I had to go to come to the university. This is the research.